Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of Fundamentals of GPU Architecture, we're going to be continuing on looking at the core architecture. This time we're going to bring up where we left off last time, which is this idea of SIMT deadlock that comes from the fact that we have this stack-based architecture. So this is something that's been, removed, or at least, to the best of our knowledge and to what we can surmise by what Nvidia's released and what Nvidia's patented, as well as kind of what the contemporary look at research is saying, is that, starting in about the Volta GPU architecture line from, 2017 onward, they don't use the SIMT stack-based implementation for divergence. So they use something else for handling warp divergence and synchronization. So, what we're going to go into today is, this idea of what is SIMT deadlock and how does that stem from the architecture, and then how we can avoid it. So we'll go ahead and start with a very simple example that shows the problem in these architectures with the SIMT stack. And so, what we're going to look at is, we'll have, we're just considering a single warp at the moment. So we'll have a single warp that, it'll initialize a shared variable. That'll just be some mutex lock to 0, 0 indicating that the lock is free. Then every thread will also do a atomic CAS, which just stands for atomic compare and swap. So this is actually just a compiler intrinsic that gets translated into this atomic.global.cas PTX instruction. And so kind of logically what this does is it will read whatever the, so it takes 3 parameters. So it will read whatever the first parameter is, which will be, say, a mutex lock. It will compare the value to the second input, which in this case will compare it to 0. 0 just meaning that the lock is free. So if that ends up being true, so if the mutex is 0, then we'll go ahead and swap that value with the value of the mutex, what we want to change it to, which will be the third input, which in this case we'll use 1. And 1 will signify that it's that the lock has been taken, right? So we'll fix that with 1. So you may be thinking, hey, this is a multi-threaded thing. This is SIMT execution. All 3 of these, or all 32 of these threads, will be doing this atomic instruction at the same time. Well, this is an atomic instruction, so they act a little bit differently. So in this case, when we have multiple accesses by atomic cast to a single location made by different threads within the same warp, they're going to be serialized. So that means that only one thread has the potential to get a lock at a time within a warp. So also only one thread will ever see the value of mutex being 0 at a time, because like I said, they're serialized. So only one of them will, that 0 equals 0 will be true, and it'll swap in that 1. Everyone else will see that the value is 1, so it won't get the lock. And so it'll just have to wait around for it. So let's go ahead and jump on down to this quick example. So this actually shows off this, what we've been talking about. So all 32 threads start out right here. So, all the threads are, no one's diverged, everyone's kind of doing the same thing, and they just all write 0 to mutex. It doesn't really matter that they're all writing to mutex. They're all writing the same thing, so it's fine. So the part that where SIMT deadlock comes in is right here, so this while loop. So this while loop is just basically an infinite loop where it says just wait until you get the mutex lock. So, like we said, this atomic CAS instruction will be serialized for all the threads. So, 31 of the threads will stay in this while loop, and then one of these threads will get out of this while loop. So you can see right here that this is already going to be thread divergence, right? So 31 threads are staying in a while loop. One thread is out of the while loop. So if we think about this from the context of the SIMT stack architecture, what's going on here? So we have a while loop right here, and so this will get translated into compares and branches. So basically what's going to happen is we're going to go down 2 paths. One that is if this doesn't, or this is true, so we didn't get the lock, So we're going to stay in this while loop, and then one where it's false, right? So we'll use 0 to say false. So if we get on the false side, we exit out, right? And what happens is we end up getting this this kind of funny, pattern where, as soon as we get out of this while loop, that's also our reconvergence point. So everybody will eventually get out of this while loop. So our reconvergence point, so if we think about our entry in the SIMT stack, everybody will eventually reconverge right here in a normal SIMT stack-based architecture. Now the problem with this is that this reconvergence point is before the lock free. So why is this a problem? So the problem is that as soon as the thread that made it past gets to the reconvergence point, its entry will be popped off the stack popped off the SIMT stack. And what will happen is that we'll resume execution for, say, the other 31 threads in the while loop. Now, this leads to kind of a cyclic dependency. So the one thread that just broke out of the while loop but hasn't executed this atomic exchange, it's going to be waiting because it wants to reconverge with the 31 other threads. But then the 31 other threads are also waiting because they need the lock in order to proceed. So we have the cyclic dependency. So, this is what we call a deadlock. So deadlocks are just where, nobody is able to make forward progress. And so basically our entire program seizes up. So that's where this kind of stems from. So, based upon, a patent that Nvidia has from 2015, kind of the research seems to pretty well correlate with what Nvidia said, and then also this patent finding. So we'll go ahead and go over kind of what they've proposed. So here we've got a couple figures. So this comes from that patent filing in 2015. We've got this example that we'll be going through from one of the research papers, and then we also have another figure that comes from the 2015 patent. So let's go ahead and start talking about how we can replace a stack-based architecture with something else. So we're going to start with those fields from figure 3.6 up here and what these actually mean. So what is a barrier participation mask? What's a barrier state? What's a thread state? Okay. So right here. So these are all fields that are going to be stored in registers and used by the hardware warp scheduler. So they're going to determine who's going to be doing what at what time. So we're going to have barrier participation masks, and these are going to be used to track which threads within a warp participate in a given reconvergence, a given convergence barrier. So this is just saying we're going to have some masks that they're going to be the size of warp, so they're going to be 32 bits. So for if say half the threads are going to reconverge at a certain point, maybe it's the first half of the threads in a warp, 0 through 16, those bits, or rather 0 through 15 will all be ones, and then 16 through 31 will all be zeros. So we'll have some mask saying, who's actually reconverging here? Who do I have to wait for? So that's the first thing. We need to know who we have to wait for. Then, in the common case, threads tracked by a given barrier participation mask will wait for each other to reach a common point in the program following a divergent branch, thereby reconverge together. So that's going to be these convergence barriers. So how do we support this? So not only do we need to know which threads need to reach this point, we use this barrier state field, which is used to track which threads have arrived, right? So this is just keeping track of, this barrier participation mask says who's going to arrive, and then the barrier state field says who has arrived already. And then one final thing that we'll keep track of is this thread state. So the thread state just says, for each thread, what's its current state. So is it ready to execute? Is it blocked at a convergence barrier? So is it waiting on other threads to arrive at some certain point? And then again, we also need to track which one is it waiting at, because we can have nested conditional statements, so we need to support having different levels of convergence. And then there's also this idea of yielded. So this is something that's a little more abstract, but we have a fairly good idea from everything that NVIDIA said and from the patent to kind of know what it does, at least at a very kind of hand wavy level. So what it appears that this yielded state does is that it may be used to enable other threads in a warp make forward progress past the convergence barrier in a situation that would otherwise lead to a SIMT deadlock. So, in order to avoid situations like we saw up here in this example, maybe we can start executing instructions, past a convergence barrier, so we could get an instruction to release a lock so that we don't wind up in the SIMT deadlock scenario. Okay, so again, since a warp has 32 threads, we're going to need a 32-bit wide participation mask that just says, hey, who's going to converge at a certain point. So here we can see kind of how that looks like from a high level. So here we have a basic example where we've got a number of basic blocks. So we've got basic block A, which is basically our entry to the function, and then we split off into two separate basic blocks, one inside of this if statement and then another inside of the else statement. So we'll have this is one level of divergence. Then within this else statement, we could go into two different basic blocks, D and E. Then we have our first reconvergence point at basic block F, where the else block reconverges, and then we've got our final reconvergence point at this basic block G, so where all the threads should be kind of getting back together at this point. And then we see that here, right? So we have 510 corresponds to this basic block. 510 basically corresponds to that first if statement. So in that if statement, we can either go one of two directions, if and else, and then inside of that else statement, right, we'll consider this the else block. That else block also splits into two different control flow paths that end up both converging at the same point later on. And so this really all comes down to this this branch based on a predicate, right? So we're branching based upon some value. For some threads it may be valid, for some threads it may be invalid, so we could go one of two ways. Same thing with this branch right here based upon this predicate 0. Okay. So so these correspond to the two if statements. So like we said, at any given time, each warp may require multiple barrier participation masks to support nested control flow. These registers that we're talking about, so keeping track of who's reconverging, what the status is, whether it's or who has arrived, whether or not they're waiting on other people, or whether or not what's the next PC that they're supposed to execute next, or they're ready, or whether or not they're being told to yield with whatever actual semantics that means. So where does this actually get stored? So these could be just implemented using general purpose registers or dedicated registers, or some combination of the two. So the actual patent doesn't say, so this low level detail is kind of abstracted away from us. So we can do our best guesses here, but at the end of the day, they're just going to be guesses. So, given that the barrier participation mask is only 32 bits wide, because like we said, 32 bits in a warp, it would be redundant if each thread had a copy of a barrier participation mask. So, if we're going to have, we could just have one 32-bit register for all 32 threads, right? Because they really only need 1 bit. They don't need an entire register. Each, that is. So, okay, so, it would be redundant if each thread had a copy of barrier participation mask, as it might if naively, using the general purpose register file to store it. So, control flow, though, can be nested to arbitrary depths. So this presents kind of an issue. So given more, maybe need an arbitrary number of barrier participation masks. So software management is a little more amenable to this situation, right? Because, asking hardware to manage something of arbitrary, depth, that's asking a little bit much. So getting a little more into the weeds, though, so kind of moving past that. So how does this actually look? So how do we initialize, say, a convergence barrier? So this is actually done with a special add instruction. And then all threads that are active when the warp executes this add instruction have their bit set in the convergence barrier indicated by the add instruction. And so we can see this in the example above. So let's go there. So here we have, right, so let's get rid of these arrows real quick. So like we said, we're going to be, we have some if statement here that we could either go into the, this would be the if block, and then this will be the else block right here. And so we know that from the predicate in this branch, but this add right here is saying this is going to initialize, who is going to converge. So everyone that's active at this point, and we'll just assume at this point it's all 32 people or all 32 threads, right? And we'll just give it some label 0. Okay. And then down here, you see we've got another label, right? And so in this time, when we do this add, for this other, boundary or this other convergence point, it's not going to say be, all, 0 to 31 threads here, right? So we really are only talking about maybe a subset of these threads that will be, tracked now, because there'll only be a subset active in this side of the basic blocks anyway, right? So some of the threads will go to the if block, others will go to the else block. And we just use these special add instructions to say, hey, this is who's going to be waiting at this convergence point that we're going to call label 1. Okay, so then the next thing we have is a special wait instruction. So this is just used to stop a warp split when it reaches a convergence barrier. So as described in the patent application, so that 2015 patent, the wait instruction includes an operand to indicate the identity of the convergence barrier. And so the effect of the wait instruction is to add the threads in the warp split to the barrier state register for the barrier and change the thread state to blocked. So basically we're combining all the threads and everybody's we're putting them in the blocked state, saying that they're all just waiting at a convergence barrier now. And so we can see that here. So at our first convergence point that we hit right here, you see we've got a wait on B1, and B1 was the this barrier that we had, coming from this basic block, and then up here at this very first one, where we call this, say B0 right here, that we initialize this this reconvergence point, we've got to wait B0 down here at the very end. So this is going to be, the very end of this this simple example right here when we're reconverging into basic block G. Okay. So that's really the basics of how that really works. So one thing we didn't go over though was yield, right? And so that's still fairly vague, so we won't go into it in right here, but you can find out a little bit more about yield in the actual patent filing itself. And so one of the things that this yield does is, it enables switching between warp splits, right? And we'll go into that, of what that actually means, but we're not going to go into, saying what does yield actually do when it's speculation. So like we said, it does help us do something as far as executing different warp splits. And warp splits you can think of as those different paths on the SIMT stack. From a 10,000 foot view, they look kind of similar, but with more flexibility. So here shows a simple timing example. So this is time going to the right, and then we've got this simple code, right? So from a SIMT stack point of view, what happens? So some of the threads will go down one branch and they'll be in here. Other threads will go in here, and then we'll all reconverge at this this point here where Z is. So right here we've got all the threads together. So that's exactly like we're at the very top of the function. Then we hit that compare statement, that thread ID x less than 4. So what will happen is one of these paths will be selected depending on how it's implemented. So we'll go ahead and go down one path. So we'll do A and B, and then this will get down here. That'll be a reconvergence point. So that will get popped off the SIMT stack, and then we'll start the other side of execution. So we'll do X and Y. We'll go past there. It'll hit this reconvergence point, it'll get popped off the SIMT stack and it will reconverge, and then everybody will work in lockstep together and execute Z. So that's the stack based. Okay, so then as we move on, right here, this is more the Volta kind of reconvergence of how this works from their white paper describing it. So basically what happens is, everybody's still all together up here before we diverge, but instead of having, this very strict ordering to which, what we have to execute at any given moment, we can kind of ping pong around. So because it's not a stack based where we just have to look at only the top of the stack, we can, maybe start executing A, then we can start executing X, then we can go back to executing B, then we can go to executing Y. The consequence of this, though, is that after we execute Y, this doesn't mean that all the threads are going to be together at that point. So we don't have a guarantee of that anymore. So, in this case, what could happen is that, Z could execute, but only for a subset of the threads. The threads may be coming from the if statement, and then it'll hit a sync warp, and so it'll just wait here. And so those threads will be blocked at that point. And then maybe the other side, we'll go ahead and execute Z over here. So maybe the else will then start executing Z right here. And then, both of these will get blocked. And so once they all finally finish and get together, so they'll kind of reconverge, and then finally they'll be in lockstep here. But we don't get this automatic guarantee that all the threads, will be in lockstep like we do in the SIMT stack-based approach. So that's kind of one of the consequences, or one of the things that we should keep in mind. And as you can see right here, there's an explicit, kind of function that we call to make sure that everyone's together, and that's a sync warp. And that's basically just one of the that's another interaction between thread divergence and reconvergence that we have. So of course we can't get away with talking about all the stuff about warps without talking a little bit about warp scheduling. So as we know, GPUs contain a bunch of warps, right? So the way that GPUs fundamentally work is we try to hide latency, not by instruction level parallelism, but we try to hide it by the fact that we have so much work that we have to pick from, that if somebody's waiting on, say, a long latency memory instruction, we just kind of throw them out and pull someone new in to start executing. But there's an interesting question though, which is who gets to go, or who should go. So we'll start with a very simple assumption, which is that each warp issues only a single instruction when it's scheduled, and then furthermore that a warp can't execute or issue another instruction until the first completes. This, though, will kind of hand wave away until later in this chapter. So if memory was ideal and responded within some fixed latency that we could account for, we could design a core to support enough warps to hide this latency using fine-grained multi-threading. So in this case, it can be argued that we can reduce area of the chip for the given throughput by scheduling warps in round-robin order. So this just is saying that, if we knew kind of how long memory was going to take by some fixed time, all we would need to do is have, enough instructions so that the time it takes to execute, or rather enough warps, all that we would need is enough warps to select from, that by the time we go down the line and start issuing from one warp at a time, by the time we loop back around to get back to the first warp, it's ready and its memory request is already back. So that's all that it's saying with this, this fixed latency, what that would mean. Okay. So one property of scheduling order is, so what round robin basically is it basically gives everyone kind of equal time, because it doesn't, pick one and say, we're going to execute a bunch of instructions from you. It just says, hey, we'll execute one from you, one from the next guy, one from the next guy. So if the number of warps in a core is multiplied by the issue time of each warp, and that it exceeds the memory latency, the execution units in the core will always remain busy. So basically what we want to happen is we want to be able to be constantly issuing requests such that, we're not just waiting on one warp that's, it's not making any forward progress. It's just sitting there waiting. So we want enough warps in there that we can constantly rotate them around and issue new instructions and new instructions. So again, like I said, we're trying to hide everything just by multi-threading, right? So huge levels of multi-threading. But, there's everything for a price. So there's an important trade-off here, which is, if we want to have different warps to issue an instruction each cycle, that means we need to store a whole lot of state. So we can't just throw away state if we want to get rid of a warp and start issuing from a new warp. So we have to keep that around, which means that every thread is going to have its own registers. That way we don't have to do some kind of crazy expensive context switching that would end up probably eating more time than it's worth. So, it's a balancing act, because if we increase the number of warps, that means we're going to increase our parallelism, so increase our multi-threading, but it also means we're going to increase the amount of state that we need to keep. So we're going to increase our register file size. So, if we keep increasing the amount of warps, that means eventually we'll start decreasing the number of cores per chip. So it's this balancing act of you can increase the number of warps, but that's going to eventually decrease the number of cores, considering a fixed chip area. Another big thing to really consider is the fact that this just makes the register file get really, really big. So already a register file in a contemporary GPU, register file will take up around 256 kilobytes of space. So that's already on the order of CPU caches, right? And this is just for the register file state. So that's one of the reasons why things like precise exceptions can be difficult, because it's really hard to keep track of that state, and asking to roll back that state is a whole nother beast. So in practice, while we're talking about memory, latency of memory depends on, of course, an application's locality. And one of the nice things about a lot of applications that we found, and that pretty much everybody already knows, is that sometimes round robin scheduling can be pretty good at finding locality. So where does this happen? So this happens a lot in graphics workloads. So when we have graphics workloads, typically we want all the warps to be in around the same place. When all the warps in around the same place in a graphics workload, they're typically working on the same data. And so this is really typical with, say, accessing texture maps and graphics pixel shaders. And so we can increase the amount of hits and the amount of time we're spending in the on-chip L1 or L2 caches if everyone's in the same place. But this isn't always the case, because there are situations that round robin scheduling can actually be bad for performance, and we don't actually want everyone to be in different places. So if we have kind of like disjoint data and complex data structures, maybe some really complex graph application, we really don't want a whole bunch of threads to be progressing along, because there's no guarantee that they're going to be working on the same data. Like we said, this could be some weird graph application. So in those cases, what's going to happen? So everyone's going to be touching different data, which means that everyone will be loading different data into the caches, which means we're not getting much reuse between different warps. If we're not getting much reuse between different warps, caches really aren't that big in GPUs, which means that we're not going to get any hits in our caches, or nearly zero hits in our caches. So what this work back in 2012 said was, if we have situations like this, it could be better that instead of trying to hide this latency by multi-threading, we'll actually do some throttling, right? And we'll say that we'll only allow, say, certain warps to execute, instructions. And when we do this, suddenly the amount of, diverged accesses coming out, suddenly it's really just from a few warps that maybe can fit all their stuff could be resident in the cache at that point because they don't have all this interference kicking things out of the cache anymore. And so you can actually schedule in such a way to maximize locality by doing a little bit of throttling. And so this idea was from 2012, and it's called CCWS, which stands for Cache Conscious Wavefront Scheduling. So wavefront is just AMD's term for warps. So, you could call this cache conscious warp scheduling if you want. Okay, so that's just kind of high level ideas about, warp scheduling. Okay, so that's really going to do it for this episode. So let's just do a quick recap. So starting from the top, we kind of introduced this idea of, last time we talked about the SIMT stack. This time we talked about, recent architectures are moving away from the SIMT stack. And the reason why they're moving away from the SIMT stack is this idea of SIMT deadlock. And SIMT deadlock comes from the fact that we can run into situations with circular dependencies. So new architectures that are not stack-based that can, schedule different groups of threads kind of at will. It doesn't have to go based upon some SIMT stack order. Get around this, and we saw that, it's more of a barrier-based implementation than a stack-based implementation. And we saw the basic ideas of how this kind of works out. So we talked about that, and then we also talked about what this looks like from a time perspective of what which threads are executing at any given moment. And then finally, we talked a little bit about warp scheduling, and really what this means. Okay, so that's going to do it for this episode. So next time, we're going to start the next level of, digging deeper into the SIMT core. So again, this is all part of the first section on the one loop approximation. So we'll talk more about, in more detail of a more realistic model of a GPU based upon what we call a two-loop approximation. So we're going to, GPUs have a bunch of schedulers in order to really provide, this really good performance. So we need to, gradually work our way up, starting from, a GPU with a single scheduler to, 2 schedulers or so, to even 3 schedulers. But like I said, that's going to go ahead and do it for this episode. Feel free to check me out on github.com/coffeebeforearch. I've got all the code for all my other series there. Take a look at my other series on YouTube on cache coherence and memory consistency. And of course, if you have any questions, feel free to message me and I'd be happy to help you through anything. But that's going to do it for today. I'm Nick from Coffee Before Arch, and I hope you have a nice day.